Good afternoon to one and all present here. I am Dr. P Jawahar, working as Professor and Dean of Faculty of Technology at Kalinga University, Naya Raipur in the state of Chhattisgarh. Let me explain about a few thermodynamic cycles in this subject which we will be studying in the subject applied thermodynamics. The first one is the Otto cycle. So it is a cycle which is basically employed in a petrol engine. In other words, it is called as a spark ignition engine. So it consists of, like most of the thermodynamic cycles will contain four processes. But of course, there are cycles which is having even five processes also, like dual cycle. So as far as the Otto cycle is concerned, it has four processes. The first one is the isentropic compression. So where the air is isentropically compressed. Isentropic compression means reversible adiabatic process. So where the pressure and temperature at the end of the compression process, let me explain before that the various strokes in a petrol engine. There are four strokes are there. One is suction stroke, compression stroke, power stroke, and exhaust stroke. In suction stroke, the air fuel mixture is taken, and it is the inlet valve opens, the exhaust valve remains closed, and the air fuel mixture, due to the pressure difference, it is supplied. It is admitted into the cylinder. At the end of the suction stroke, the air fuel mixture is compressed as the piston moves from bottom dead center to top dead center. So at the end of the compression, the spark plug is used to produce a spark, due to which the combustion takes place. That is, the carbon in the fuel and oxygen in the air reacts. And if it is a complete combustion, carbon dioxide is liberated. And if it is a partial combustion, we get carbon monoxide. Of course, both are affecting the environment, both are pollutants. Then at the end of the compression, once the spark is ignited, produced by the spark plug, due to the force exerted by the gases on the piston, it makes the piston to move from TDC to BDC. So that indicates the power has been produced by the engine, by the cylinder of the engine. So, and the exhaust gases which are there in the cylinder, it has to be drained out from the cylinder. So the exhaust gases are pushed by the piston from the bottom dead center to top dead center. And during this process, the exhaust valve opens, and these gases are sent, and the next cycle commences. The next set of air fuel mixture will be admitted through the inlet valve. This is the process. So when we when we take the Otto cycle, it is a air standard theoretical cycle. So where the process, normally the suction process is not mentioned in the TS diagram or PV diagram, whereas the other three processes, compression, expansion, exhaust, all these things are this one. So the first one is the isentropic compression, where the air is compressed isentropically. That is, other name for isentropic is reversible adiabatic, from process 1 to 2. Then 2 to 3 is constant volume heat addition. That is constant volume. That is the combustion process. 3 to 4 is reversible adiabatic expansion process or isentropic process. What happens in the Otto cycle during the process 2 to 3 is the volume remains constant. And during the expansion process, obviously the pressure and the temperature drops. Expansion process is just opposite to compression process. During compression, the pressure of the working fluid and the temperature of the working fluid both increases, and during expansion process, both the pressure and the temperature drops. And the maximum temperature is attained in the cycle at the end of the combustion process, just before the expansion commences. And the process 4 to 1, 1 to 2, 2 to 3, 3 to 4 is completed. 4 to 1 is the constant volume heat rejection process. That is, primarily we are referring to the exhaust stroke, where the exhaust gases are sent out from the cylinder, which is present inside the cylinder, to the atmosphere through this exhaust valve. So if we want to define the efficiency of the cycle, the efficiency is the output by input. That is, heat supplied, how much is the heat supplied, and heat rejected. That difference is the net work produced divided by heat supplied. So that is QS minus QR divided by QS. When we derive that one, we will get the efficiency in terms of compression ratio and gamma. Compression ratio is the volume of the cylinder after the compression has taken place, at the end of the compression to the beginning of the compression. That is the compression ratio. Normally for petrol engine, this value is in the range about 8 to 12 or even 14, and for the diesel engine it is in the range from 12 to 18. So this is about the Otto cycle. The theoretical, it is a theoretically air standard cycle which is used in the petrol engine. Now let us make a comparison between this Otto cycle and diesel cycle. There is only one difference between the Otto cycle and the diesel cycle in terms of processes. In case of Otto cycle, the heat addition takes place at constant volume, whereas in diesel cycle, the heat addition takes place at constant pressure. So process 2 to 3, instead of if we plot it on a pressure volume diagram, in case of Otto cycle, the line will be perpendicular to the x-axis because constant volume process. In case of diesel cycle, process 2 to 3, the line will be perpendicular to the y-axis, which is pressure. Pressure is on the y-axis and volume is on the x-axis. So similar to the Otto cycle, here also we have 1 to 2 is isentropic compression, that is a reversible adiabatic process. 2 to 3 is, instead of constant volume, we have got constant pressure process. And 3 to 4, similar to the Otto cycle, a reversible adiabatic expansion, that is the power stroke. The other name for power stroke is expansion stroke or working stroke. And 4 to 1 is constant volume heat rejection. There is no change in the constant volume, this one. In diesel cycle, the heat addition is at constant pressure, whereas heat rejection is at constant volume, which is similar to the Otto cycle. Now let us move to the third cycle, which is existing only in theory. It does not exist in practice. That is the dual cycle. It is a combination. In one way, it is a combination of Otto cycle and diesel cycle in terms of heat addition process. This thermodynamic cycle is different from the other cycle in terms of number of processes, because most of the thermodynamic cycles have 4 processes, whereas this dual cycle comprises of 5 processes. So instead of 4 processes, we have got 5 processes. The process 1 to 2 is, as usual, isentropic compression of the working fluid. 2 to 3 is constant volume heat addition. First, the heat is added at constant volume partially. Then the remaining heat is added at constant pressure. It is very difficult to construct an engine or a cycle in which the heat addition can take place both at constant volume and at constant pressure. So that is why this is existing in theory, and there is, of course, there are other reasons also because of which it could not be converted into practice. So heat addition takes place at process 2 to 3 at constant volume, and partial heat addition takes place at a constant pressure 3 to 4. So 2 to 3 will be perpendicular to the x-axis, which is volume, and 3 to 4 will be perpendicular to the y-axis, which is pressure. Then process 4 to 5 is the isentropic expansion, that is the reversible adiabatic, which is similar to process 3 to 4 in Otto cycle as well as in the diesel cycle. So this is the expansion, that is the power stroke. And process 5 to 1 is similar to process 4 to 1, which is there in the Otto cycle and diesel cycle, which is nothing but the constant volume heat rejection. So here also the heat rejection takes place at constant volume. So if you see the net heat addition, heat is added during process 2 to 3 at constant volume, and the heat is also added at process 3 to 4, which is at constant pressure. So the heat supplied is a combination of both constant volume, mCV delta T, and mCP delta T.